That's also filling out how, this is the first time I've been in class years where you've actually given quizzes, you know?
Yeah, and I'm not a big fan of quizzes, but I'm doing it because it's an integrity thing and it's been a problem in the past, particularly when this has been a very large class, like up to close to 40 people in the class. So I could do away with them, but I don't know if I want to do that. Okay, so I'll tell you a little bit about the quiz, but I'll tell you a little bit about some things I added to the website before I get into that stuff.
Did you say you're going to get into the quizzes?
Yeah, what I'm going to do is I'm going to put up the histogram of what the quiz scores were, so you know what the numbers mean. I added, I took Colton's recommendation or request, right? So now we have cumulative pages being posted. That's what you wanted, right? If you've looked?
Just at least so that everything's on one page.
Yeah, so the quizzes will, not the quizzes, but the homeworks, I'll post the homework up. When I add the hints, I'll just add those below it. And when I add the solutions later tonight, I'll add that. So it'll be one document. They'll be locked, though. Only the homework document itself will be unlocked because, and I've said this before, but just to reiterate, I do that not for you guys, it's for the world, because the world can see my site. So I'm trying to preserve the integrity of the homework solutions and everything else for other people using the book. And faculty actually have to sign something. I mean, maybe not on paper, but we have to agree to an agreement when we get a solutions guide. And I don't use the solutions guide that much, but it's the idea of putting up book answers in general. The other thing that I did, though, is I ended up, because of my phase lock loop class needs the interactive note graphics in the Jupyter Notebook, I did some more exploring on that. So I added something to our home page. It's not on the other home pages yet, but it's this link that says configuring Anaconda in virtual environments. So we've looked at this before, but now when you click on it, since I've added more stuff, I used Typora. Remember Typora when I went through that? I put in a table of contents and I had it export an HTML file from Markdown. So that's the cool thing about this new technology stuff with Markdown and other languages. So I exported this and I added some figures into it. And I also had to exercise in the process of doing this on this laptop, not my MacBook or my other Dell system, but my whole Anaconda installation went haywire on me. And since it was a virtual environment, which is based out of Miniconda, all I had to do was follow my instructions and build a new virtual environment. I still haven't blown away the old one that got all messed up on me, but I'm just telling you that I do this stuff for you guys and for me, and I need to have a cheat sheet tell me how to do it. So I rebuilt one yesterday. I haven't, like I said, I haven't deleted the old one, but I will. But lately, Matplotlib has been improving its plugin for Jupyter Lab, and it's called IPyMPL. So it's IPython, which is for the widgets, IPython widgets, and MPL is for Matplotlib. So when you install that, and I've got a link that talks about it a little bit, you install it using Conda, and it's very important if you go ahead and give this a try that you have to point the Conda installer at this particular repository, because otherwise it pulls up an older version, which doesn't work or didn't work for me. And some of you that have been in my office, when I helped you, I was doing things under these command line options. And what it is there's a cloud of repositories out there for Conda. Conda Forge is the primary one, but there's other repositories. So if you don't point it at one, it goes looking, and if it finds something, it puts it on. But if there's a newer one, it might be on a certain repository. So this was recommended in a blog, and it made a huge difference because the version was newer. But once you get it installed, then you have to install the lab extension and so on. And this this has probably already been done for most everybody because they gave you that instruction, but you have to install this extension. So what it looks like when you get done, if you install the plugin manager, which the little easel here with the color panel on it, when you click on that, if you don't have it installed already, under Jupyter Lab, not Notebook, but Jupyter Lab, it's called the extension manager, and when it's enabled, then it puts up this little puzzle piece to represent plugins. And what we're talking about is this is the native plugin that I want you to install, Jupyter Widgets Lab Manager. And then I've installed the table of contents. But once you want to get this interactive plot tool working for Matplotlib, then this will get put on. And if you happen to get this installed, you can type other things in the search box, and it will let you see other plugins that are out there in the community. There's a lot of them. I've been following this since before it came into existence, and it was pretty exciting when they first announced it because it said, community, respond, build plugins so that your Jupyter Lab can be better. And that's one of the cool things about the open source community. People don't work only for themselves, they work for the community. It doesn't mean they don't create junk that you don't want, but you have to go exploring and read blogs and things. So it's now installed on my system. It doesn't work quite right on this one. I don't know why. It works great on my other two machines. Right now, though, I'm just telling you, it is kind of still hit or miss, and I really feel it's a statement a little bit about open source software in that 2 out of 3 ain't bad. I guess it doesn't sound good if you're on the losing side of the installation, but maybe a new install would clean it up, and I just spent too much time on this yesterday, but I'll show you what it does in the screenshots I took. So once it's on, rather than putting %pylab, which is a magic for the Jupyter Lab that tells it to load Matplotlib and NumPy, fill your workspace up with all of those function links. Then you put inline for the normal inline graphics. The alternate is IPyMPL, and that's what I have set up when I did the screen capture. So now when you create a figure, a plot, it will bring up these interactivity items in your figure window. And if you want to put Seaborn style in, I did that. That just is a different colorization, but that's another package that's really popular amongst data scientists in particular. And then third, I put Plotly down at the bottom here, but I did put an example. Plotly's a lot more work to install. I wrote a helper module for it that's not available in the Scikit DSP.com. It's not installable right now, but I can send you the .py file, and if you just put that in a folder where you're running your notebooks, then you'll be able to load Plotly helper. And what it does is it gives a simpler command line for creating a few different types of plots. Plotly is very rich, but it has a lot of syntax that you have to put in a cell to produce a plot. So this makes it easier, and it's got all of these interactivity widgets in here, right in the notebook itself, and the graphical display, and then you're hovering around on this stuff, and this is called spike lines, is what they call it. And as you hover around, you can get the exact coordinate of where you're sitting. It's still better than Matplotlib's interactivity, but Matplotlib is kind of the traditional graphics engine to go, plotting engine to go with scientific Python. I'm telling you all these things because MATLAB is a closed environment, so you really don't have any of this kind of stuff, and all open source things that I've been involved with and utilize always come with a lot of things because people in the community feel inclined that they want to do something to make, not to make a name, but they just say, I want to make it better. So they make it better and then they share it. So it's just kind of the way that it all works out. So I'll show this to you a little bit later, and maybe it will work okay, but maybe it has a little artifact that I'm not particularly happy with on this machine, like I said. Meanwhile, we're going to get back into this, but I'm going to now bring up a blank page. So so that I can at least show you what the histogram looks like. Make 5 blank pages.
Real quick, I have about the homework,
I'm going to get to the homework too.
one of the commands that we used for, I just closed it, for doing the stem plots
Yeah.
was given the, when we use the sides equals 2, part, it gives you a whole invalid sides chosen, and no matter how I configured it, I don't know if that's something you've come across, but I couldn't find any
No.
information on
I
online.
know you have to put the use whatever equals true. That's something that just came up last fall.
Yeah.
But you're trying to make the size of the tops of the stems bigger or smaller?
No, it was just the sides, not sides.
Oh, sides.
So it was a double-sided spectrum plot.
Okay.
It was giving me, it gave me an error for every iteration I ran through.
Hmm. Well, I've got examples of doing that in the Chapter 2 notebook, so we'll maybe look at that. Okay.
So,
Maybe you got an issue with your installation. I don't know, because I haven't seen that problem there.
yeah, there's no reference to it online, so I was seeing if you knew anything about it.
I don't.
You don't,
There's always something new.
right?
Does anybody in here watch Saturday Night Live comedian show ever? I was in college when that TV show came on the air, so it's been a long, long time ago. But there was a actor in the first series, the first couple of years. I forget what her actor name is. I'll think of it. Her name on the show was Rosanna. Maybe you've seen the old reruns, but her skit every week, she was usually on talking about something really bizarre, but her saying was, there's always something. If it's not one thing, it's another thing. There's always something. And then she would go on and tell a story about, you know how it is when you do this, something really gross usually, like pulling something out of your nose or whatever. And she'd go on and just, but that was her thing every week. Her saying, her byline was always, there's always something. If it's not one thing, it's another thing. So that's true in software, I think, too, right? There's always something that you want to make better, and then you try to fix that and break something. So, quiz number 1, now, just to give you the histogram idea, there's 2 at 37, 34, 1, 32, 1, 25, 1, 24, 1, 17, 1, 15, 1. You can average that up. I didn't take the time to do it. It's in my spreadsheet, but I haven't written it into the spreadsheet yet. It's on my copy of the spreadsheet. Quiz number 2. One person got a 30. One person got a 22. 2 got 21. 1 got a 16. 1 got a 15. 1 got an 8. No, a 9, excuse me. And 1 got an 8. So, since I just graded them over the last couple of hours, some of you were suffering from shell shock, I think. You just almost didn't know what to do, and that's not a good thing, right? You got to be in motion. You got to get some momentum up. So others of you, though, who were creative but still didn't quite get the right thing done.
Just out of curiosity, is it the problems that you give us answers to that you expect us to be able to do on the quizzes, or is it the other way around, the homework assignments that we turn in?
The quizzes are more reflective of exam problems because
Yeah, no,
they're
but-
done with your pieces of paper and a calculator. Whereas the homework problems are more realistic types of problems where you get to use all the tools that you would normally use if you were working on a job somewhere.
I think over the past couple of times he's named specific problems, but for the most part I didn't see any of them that correlated to the ones we turned in.
Okay. Thank you.
So
Okay.
basically we have to do the whole thing.
Yeah.
Well, I tell you what the themes are, though. I mean, yeah, the homework problems are generally longer than what I think a quiz would be. So that's why I say there's certain themes, though, that I'm looking for. So I have a large repository of old quizzes, so I go looking in my repository and decide what I want to go for, and then I make something new or rework something. Okay. Enough about that. If I had a grader, yeah, the papers would be graded, but I don't deserve a grader, so, because I don't have enough people. If I had a grader, though, then some of you are probably grading, right? And you've graded before.
No.
You've never graded?
Never have.
Okay.
But
When you grade, you don't know what mess sometimes a grader creates for the professor when the papers get handed back, and then people are like, what happened here? And then I have to go mediate between the student and the grader. But it's challenging. It is far better if I can do it, because then I see everything. But when you're got a lot of papers to do, you have to farm it out, and it's very helpful. But I'll tell you one thing, I'm a lot more in touch with what's the pulse of the class when I'm doing everything myself. It's just like anything, though. You can't micromanage everything, but right now, that's where I'm at. I'm the head of the power system search thing, and we met Friday during the snowstorm. We got our resume count down from 100 applicants down to the top 10. So we have the top 10 that we're simmering on, and we'll start the process of doing the phone interviews and that kind of stuff. But that was daunting. I stayed up pretty late. Other committee members stayed up really late too.
You should do something like a survivor challenge or a fear factor competition to weed them out a little bit further.
How? Well, you guys are going to be sending resumes in, or you already have put resumes in. One of the things I notice anymore, because of electronic submissions, people don't read the minimum requirements. They just submit something.
Mm-hmm.
We get it. The first thing we have to do is see, are all the minimum requirements met? If they're not, it gets a 0. It gets scored a 0, and it drops out immediately. We had a fair number of those, but then you have to look more carefully and kind of weed your way through different things. But there's a large percentage anymore that are just totally from nowhere. Actually, you see, we were on a search committee last year for Dr. Semiari, and I was on that committee as well. And we had Donald Trump submitted a resume, just as an example of goofy things that people can do. It wasn't a complete dossier, but it was a partial, I don't know. It's just between Dr. Platt and Dr. Trimboli and I, because we were on that committee together, it's kind of a joke about, we didn't have it, at least we didn't have one of those types of submissions this go around. And you'll be on the other side of this someday too. Once you're a more senior engineer, you'll be slaving through this stuff. Okay, last time we made pretty good progress, but not enough to make the homework super smooth, so I've got to blast ahead and get to that point. We're very close though. Fourier transforms of periodic signals can be looked at in the Fourier transform domain by just simply using the Fourier coefficients and then locating those spectral lines using the delta function. So that was kind of the big innovation with the Fourier transform and the limit. And these were some of the various transforms we took a look at once we got into it. The idea that we can allow delta functions in the frequency domain. This one right here, super important. I mean, how would a signals person in communications how could they survive without having the spectrum of a cosine? And it'd be nice to have it in the Fourier domain. So here we have it. We have the two delta functions locating it conveniently. We have the phase gets located and so on. And then this kind of wraps that around that to say, okay, it's really the Fourier coefficients are identifiable in that sense. Talk through a little bit about this. This is just how the synthesis works. It's saying, how do we go from line spectra back to the time domain? We're summing phasors. That's the Fourier series synthesis formula. And then if we have continuous spectra, we would just integrate this expression right up here. We just inverse Fourier transform that, and the sifting property, the delta function, is just going to sift out what's going on here. I mean, let me just demonstrate in case you're wondering what I'm talking about. If we wanted to inverse Fourier transform this, we would go e to the j 2 pi ft df, right? And then we do our engineering thing of moving the integral inside of the sum, and then each of those individual integrals with xn times delta of f minus n f naught is going to give back to you x of n times e. Replace the delta function hits, namely where f is equal to n f naught, we're just going to pop out with e to the j 2 pi n f naught times t. And of course that will end up doing that, and that is the synthesis formula for Fourier series, right? You resynthesize the waveform given its coefficients. What we need to do is be able to go in the other direction. We need to figure out how to get that xn, and that is coming up shortly. So that's this. To motivate that, though, Dr. Ziemer has in the book an intermediate step, and that is just developing the Fourier transform for an ideal sampling waveform. Ideal sampling waveform is this. It's an impulse train in time where you get a delta firing at every t sub s seconds. This waveform is useful when you're discussing sampling theory and wanting to represent an ideal sampled waveform. I mean, it's used in modern DSP. It was used in that class, which Chris was in last semester. It doesn't get used in 2610 when you learn about sampling theory, because when you first learn about sampling theory, you haven't even heard about the Fourier transform yet, and delta functions are something that you haven't really gotten exposed to, so they keep things at a lighter level in that class. But you know, as you move up in your courses and so on, the math gets a little bit heavier and you're more mature, and the theory is that you can now deal with it because you're going to grow up. I mean, and that's true in general. I mean, if I would have had you in 2610, I probably would have seen a lot different expressions and a lot different attitudes. It happens really fast is what I've observed. And I guess since I was really young at one time, everybody always would kind of make comments about, you're so young, blah, 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 this. And you don't really want to think about that, right? When you're growing up, you're kind of embarrassed when somebody points that out to you. And so I think engineering students don't want to really remember what it was like their first semester or their first week in a class, because it's like, I don't even want to think about that. I was young and naive, and I don't want to remember it because it's just something I want to just not talk about. Has anybody ever felt that way?
Feel pretty good being 20 to 4,000 level tech elective.
Okay. But I remember how intimidating it was for me in a circuits class, and we used circuits when I was in getting my undergraduate degree as the weed out class for just about all kinds of things. I mean, it was very intense, and I had a Japanese professor for 2 of the 3 classes in circuits, and his English wasn't the greatest, but he was very intense and mean sounding, and he was blowing people away right and left with the material. That was just the way he operated. And I had him for an advanced circuits class, and I remember he brought his daughter in. She was quiet. Somebody fell asleep during that final exam. It was the last day of finals week. This was in Upper Michigan, where everybody had to commute at least 5 hours to go back home again. So people wanted to leave town, but I had to stay till Friday. And I will never forget is how somebody fell asleep right on top of their exam paper during the final, and our time was up, and we were packing up to leave. And he told all of us, be quiet, don't wake that person, just let's quietly leave the room. That person will know where they need to go when they finally do wake up. But I'm not sure they could go anywhere because it was late Friday afternoon, the place was closing for the break. But I don't know what happened to that person, but does that sound like a pretty mean thing? Fall asleep on your final and don't get to turn it in, and then they don't even wake you up to say, time's up. I learned to respect him a lot, though. Okay, so we want to Fourier transform this pulse train. So now we have the ability to Fourier transform a delta of t, because that was one of the results that we had over here. We have this result right here. Actually, it was stated up there in the, well, it's stated somewhere in here. So we can transform those one at a time, but then we also have the Fourier, we're after a Fourier series representation. So that's kind of the trick here. You say this is a periodic impulse train, so you're going to find its Fourier coefficient from the Fourier coefficient formula, and you solve for that coefficient for a given value of n, and you find out they're all the same. And when you put that into the Fourier transform formula that we were just talking about, and you put it inside of this guy right here, with the impulses now in frequency, you finally arrive at this transform pair, which says that you're just Fourier transforming the complex sinusoid, and that's a delta function in the frequency domain, and then you have this impulse train in frequency. So you end up with this mathematical Fourier transform pair, which shows up in the table that you have for in your crib sheet, and then you have this picture that I drew out that just says both are impulse trains. One's in time, the other's in frequency. So this ends up being a useful result because we're going to be wanting to do an expansion. So, and that expansion involves using convolution, the convolution theorem. So now we have this theorem, and this is, or this transform pair, and this is one of those three special transforms which I learned about when I was a graduate student teaching signals and systems from the senior faculty. They said, give them that question. Ask them what are the three signals whose Fourier transform are the same as the signal itself, the same form. Remember I talked about this? One was 0, Fourier transform of 0, 0. Fourier transform of a Gaussian is a Gaussian shaped function in frequency. Fourier transform of the impulse train in time is an impulse train in frequency. I'm not going to ask you that question now. I just think it's a novelty kind of thing now, but it's kind of cute in that way. At any rate, now we can use that. So now we're going to say, let's generate or represent a periodic signal in terms of an impulse train in time. So that represents a periodic signal. Convolve it with a pulse shape p of t, and then that is going to replicate the p of t pulse up and down the time axis, because every place the delta function fires, it will locate that pulse function p of t there. So that's what this would be right here. So that's cool. We can generate a periodic signal using one period of the waveform and then plopping it down on the time axis with this impulse train. But then what we do is go to the convolution theorem. So this is, that's convolution, so we know when we go to the frequency domain, Fourier transform both sides. We can take the Fourier transform of the impulse train times the Fourier transform of the pulse, and that's the first line here. And then it's fair because the impulse is 0 everywhere except where the impulse turns on, so it's fair at this point to just simply take that guy and put it inside and just sample it at n times fs. So what it's representing for us is it's saying this is the Fourier transform of a periodic signal. And that's kicked off in the very first homework problem of set number 3. It's a drill problem, right? It's got triangles that are spaced periodically along the time axes. The other thing that I didn't say there, though, is but if you look at fs times pn NFS. That actually is the Fourier coefficient that we were seeing it previously. So Fs is a scaling factor. That's the same as the period, by the way. And I just used Fs because that's what the book was using. But this is the same as F naught, which is the fundamental. So that's kind of nice to know. And this gets talked about in Lab 2 as well when you're doing the spectrum analysis in the lab. So I took one example here, and there's other examples. This property gets applied several different times in homework set number 3. So I want you to understand this. There will be a quiz question on this sometime. I don't know whether I should do it this week or back up with some problems from last week's quiz for this week, but you will certainly have this on a quiz, and it will show up, the application of it will show up in the first exam as well. Because I think it's so convenient. I didn't learn this when I was an undergraduate, but I learned it from my advisor, Roger Zemer, so he's the one that introduced me to it, and I think it's just great.
And by this, do you mean the example or the highlighted equation?
The blue equation, how useful that is.
The Fourier transform.
Yeah. And I gave you permission to write it on your crib sheet if it's not already on there. I mean, you can add that to your crib sheet if you want to, just so you'll always have it. Just find probably the side where the Fourier transform pairs are. If it's not in that table, and I don't remember whether it is or not, but just add it below. Is
Only
it-
only the sum of
The,
deltas.
okay, the impulse train one is in there. So right underneath that would be a good place to have this. You just have to remember, though, that P of t is one period of the periodic signal, and then capital P of f is the Fourier transform of the one period. So you have to, this is linked in with it. So the example I picked here was just a house, 2 building blocks, one stacked on top, one stacked on the other, just as an example. So if you want to apply this theorem to get the spectrum or the Fourier transform of this periodic signal, you just simply look at one period, which, you know, once you have enough information to establish what the period is, here it'd be minus 5 to 5, would make sense as the interval for analysis. I mean, you could make life hard for yourself, and you could say that's a period. That will work in this theorem, by the way, but which one do you like better? The one that's centered on 0 is a lot easier to kind of make sense out of, because that's 2 rectangle pulse functions, right? You had a question, or you're just giving a thumbs up?
Like half a second.
Pardon me?
Could you scroll for like half a second?
Yeah.
Okay, that's it.
Does everybody see that, though? A period is a period, so if it was what I have bounded by the blue or the red from minus 5 to plus 5, I would rather do the red, because then I can just see it as a rectangle of full base width 4 and a rectangle full base width 2 stacked on top of each other. So I didn't write that in here. I just said I'm going to use this Fourier transform pair, but that would be pi of t over 4 plus pi of t over 2. Speaking of that, it's made me think of the quiz, because I did put the solutions out for the quiz, but I did find a mistake. I forgot megahertz, so I'm going to put microseconds in place of seconds, but I'll fix that. I mean, I fixed that when I graded, but I'll repost that. So then you just have to replace F. F goes to n times Fs. And then in this case, Fs is 1 over 10 because the period is 10 seconds. So you replace the fundamental frequency, which is 0.1 hertz by 1 over 10. And then you make those substitutions everywhere, and then you get this sort of an expansion. And of course, the Fourier coefficients, remember, jump off out of this formula as what's in the square brackets, and then the 1/10 out in front is the scale factor, and that makes your x of n Fourier coefficients. Just pausing for a little bit here. If you were to have this knowledge and take it back to 2610, when you first learned Fourier series, if you had your choice now, I probably didn't say that right. If you had your choice right now, which would you rather do? Have to do the Fourier integral to get the coefficients, or have the advantage that you might be able to simplify things by using this theorem? You still have to take a Fourier transform, but if it's a function or a pulse shape that's in the table, you've got a head start on it rather than starting from scratch, having to integrate. Poisson sum formula, I'm just going to, it's kind of a mathematical moment, and I'm going to just skip over that. It's talked about in the book. You can read about it. The Poisson sum formula does show up in certain applications. I'm not going to dwell on it, though. You also see that if you're taking prop and stats now, you know Poisson is in probability and statistics as well. You have Poisson random variables. Eventually you have Poisson approximation to the binomial probabilities and other such things. Some of you that have already had the class, do you remember his name showing up a lot?
Yeah. That's it.
Okay, and this last thing I already talked about, that's the Fourier coefficient. So now we've kind of covered some things about Fourier. We have to get to linear systems theory, but now we're going to insert as a review topic, but now we're going to do something totally new from your background. We're going to look at power spectral density and correlation. So the way the book gets into power spectral density is they start with energy signals. So first consider energy signals, which are easier to deal with, and then we'll move over to power signals. So for an energy signal, we know that the energy spectral density, which remember was defined earlier as magnitude of x of f squared, if it happens to be that we're talking about, say, a signal x and its energy. That's just integrating that quantity, and we were talking about units when we were doing that. Remember, we were looking at the units to see that if we have a 1 ohm impedance, that magnitude of x of f squared is indeed joules per hertz, because that makes it a density. Density means it's something per unit length. In this case, it's frequency is the unit length we're talking about. So joules per hertz of bandwidth. So for power signals, we want to have a similar definition, and this is an elusive aspect of all this right now. We can say what we're looking for. We're looking for, and if I was to put the x on here, that would maybe be more convenient. So we're talking about a signal x and its spectral density Sx of f and its total power Px. We know on the right-hand side that if we take a power signal and we do this time average of the magnitude squared, that gets us the power. And remember, it's challenging if it's not periodic, because then you have to take the limit as the time axis goes to plus and minus infinity. If it's periodic, you can do it over one period. But what does Sx of f look like? Getting a handle on that is not an easy thing, so we're going to kind of skirt around things and kind of jump jump to the answer without really getting a super clear explanation, because it's not really easy to do at this level in this course. So, but we'll have an operational definition and a way to work with, a way to get the power spectral density. And that's where the autocorrelation comes in. That's why this topic also involves correlation, because we need to have a stepping stone to get there. So we know that if x of t is periodic, the power spectrum is going to consist of impulses at the harmonic locations. That makes sense intuitively, and if you played with a spectrum analyzer in the lab, that also makes sense, because when you're on the spectrum analyzer, it plots a one-sided spectrum, but if you put a cosine wave into the spectrum analyzer and then dial the cursor over to that spectral line, the little display on the analyzer tells you what? How much power in dBm you have at that frequency. As soon as you move away from it, you don't get anything, because there's essentially just noise in the background. So you have this intuition that you're hitting a delta function at that point, and the analyzer is calibrated to tell you that that's how many watts of power are sitting there in the frequency domain. So with that thought in mind, the mathematical definitions that we use for spectra always have the positive and negative spectra. So if we think about what is the power in here, we know just from earlier discussion and circuits and elsewhere that it's just going to be, for a cosine wave, it's just the amplitude squared over 2, right? You saw this in circuits 1, I guess, 2205 probably. Am I right or not? Is that where you first see it?
It's 3205.
It's not until 3205? Okay. But you've seen it before, though. So a squared over 2. So how do we make that work if we were to synthesize a power spectral density, something as a function of frequency with delta functions locating the spectral content? We'd have to have it distributed between the positive and negative frequencies. So this setup here does that. We'd have 1/4 a squared at plus f naught and 1/4 a squared at minus f naught. So now if we integrate the entire two-sided power spectral density, we would get a squared over 2. Acceptable? I mean, this is just like hand waving, though. It's just saying this is what we want, but we want this function to come at us by some direct calculation means, not just sort of, guess beating around the bush like this. But we're going to get there pretty quickly. So now we need to jump over and think about the autocorrelation function as a means to get there. For the energy signal, not a problem. Energy signal, we can take the magnitude squared of the Fourier transform, and then we get the energy spectral density. But for a power signal, it doesn't work out that way. So first, what is the autocorrelation function of an energy signal? We have the energy spectral density, so it turns out that autocorrelation and power spectral density are Fourier transform pair for energy signals. So inverse Fourier transforming gives us a function phi of tau, and tau is used as a time delay variable. It's just saying if I have a waveform and I'm going to use my hands with my thumb as a timing marker, and suppose I take the signal itself and slide it past the signal, when the signal and itself are closely aligned, I'm going to get a strong correlation. When they slide off, weaker correlation, weaker. Hit it hard there. So for an energy signal, which is an aperiodic type signal, I would get a strong correlation. When they're aligned, it will get weak either direction. So auto means self, and correlation means establishing a relationship between something and something else. That's what people say when they say correlated, right? Statisticians use that term, and you learn about correlation in prob and stats. Correlation is actually kind of like when you take linear algebra, you learn about abstract vector spaces, and you learn about dot products and things like that. So correlation is really analogous to taking the dot product between one component and another. And if the dot product yields a large value, that says one vector is collinear with the other vector, right? That's the idea of that's how correlation comes to being as a statistical measure. It's either they're both pointing in the same direction or they're pointing in opposite directions, but they lie in the same, they're on the same line or the same line in space. In a waveform sense, though, it's saying the waveforms are alike, and when they lie on top of each other and we integrate, we get a large number. And that's what comes out of this math that I wrote out here, where you've got break g of f down to x of f and x conjugate of f. And then we go using the convolution theorem dual, where we have multiplication, convolution theorem. We go inverse transforming, and we're going to be convolving then the inverse Fourier transform of x with itself conjugated. And if x happens to be real, which is what we're assuming right now, then x conjugate of f is the flipped over signal. So we're convolving x and x flipped over. But when you put that inside the integral definition for convolution, you see a plus sign, so the signal is not flipped. And that's the difference between convolution and correlation. Correlation, again, going back to my thumbs, this is the best thing I can do standing here without trying to draw a picture. This waveform and this waveform are supposed to be identical, so that's correlation. Convolution would be that kind of thing, where one is flipped. So correlation means one waveform correlated against the other. They have to be in the same orientation. You don't flip one over. So in convolution, that's what's happening here. You get the flipping here, but then this flips again. So flipping twice puts you back in the right direction. Does that make sense? Sounds unpleasant though, right? Why would you do a convolution and then have a flipped again signal? It's just convenient because you've seen convolution before, but when you see what's in the blue box, you see, oh, x of t times x of t plus tau, so there's no flipping. It's correlation. So that is autocorrelation for an energy signal. You just slide the signal past the other one, integrate the product, and of course take a limit, so you're considering the entire time axes. So in a practical application of this, you could just get rid of that. Just like for energy signals, you could do that. And then you'd be able to say that, oh, if tau equals 0, then the two signals are on top of each other, and then you'd be able to conclude that phi of 0 would be the energy in the signal, because that would be just squaring, and we usually write it as magnitude squared just in case it happens to be a complex signal. But autocorrelation function at 0 is when the signals are too perfectly aligned, and when I integrate the product of the signal times itself, I'm getting the energy. So it's kind of cool, and that's the most correlation you can get is when it's on top of itself. So what we observe from this, for energy signals at least, we have a direct means to get to the power energy spectral density right across the top, nice and beautiful and easy. But as an alternative, we can first go from time domain signal to the autocorrelation domain, phi of tau, and then what we're seeing from this result here, we're seeing then we can go out to the energy spectral density by Fourier transforming the autocorrelation. So this I was calling the stepping stone. You have to, if you choose the lower path, you have to stop and then move on from there. Well, for the power signal case, that's exactly what we have to do. We don't have a direct path across the top. It just, mathematically, it doesn't work out that way. And I'll give you some examples of that here, or at least we'll work through some special cases. So we do have to get the autocorrelation function first and then go on, and we use a powerful theorem to do that. But the autocorrelation function for a power signal is a time average, and in particular, and these are the types that we deal with here in this class. We're only considering power spectral density of periodic signals. The other class of signal that gets considered is a random signal, like I mentioned in the very first week of class. We have a tool to get the power spectral density estimated in Python and in MATLAB, but we're not dealing with that definition mathematically in this class. That would come in Com Systems 2, and it's talked about in a later chapter of our book. There's a statistical autocorrelation function, which is based on using province stats ideas, density functions, and random process ideas. But at any rate, we have this form for the periodic case, which involves just integrating over one period. So now we have the interesting result that if we look at the autocorrelation function at 0, and if we generalize from the real to the complex case, if that goes to 0, then we have x of t times x of t time average, and just go ahead and make it the complex case. So we take the magnitude squared instead. That gives us the power in a power signal, and that's the autocorrelation function at 0, and that must be, so this is a must be in here, must be equal to the integral of this elusive power spectral density, because power per unit frequency, if we integrate all the power spectral density, we should get total power. So that is weighing heavily on us that something is going on here that we're about ready to see, and there it is. Because the Fourier transform of the autocorrelation function for an energy signal gives us the energy spectral density, intuitively it seems like the Fourier transform of the autocorrelation function for a power signal should give the power spectral density. And actually there's a theorem called the Wiener-Khinchin theorem, which is talked about in chapter 7 of the book. So this little picture down here is how you explain to go from a power signal to its power spectral density. We have to first get the autocorrelation function, and to do that we have to go through this time average definition, and then we can move on from there taking the Fourier transform to get the power spectral density. So there's homework problems in set number 3 that revolve around doing these things, but for simple signals, nothing really too complicated. And things work out and look nice. There's a number of properties of the autocorrelation function. At time offset 0, that's the maximum value of the autocorrelation function. Any other value is going to be less. And tau, I didn't use the terminology, but in statistical literature, statistical signal processing at least, I get that wrong. They refer to tau as the lag value. So again, with my hand up here, 0 lag if my thumbs are aligned like that. So you lag in the positive direction or you lag back in the negative direction. And you can see the second property, the autocorrelation function, is that it's even. So if I'm lagged like that or lagged like that, I should get the same value. My hands aren't quite the right waveform shape, though, to make it look like that's convincing, but the math is correct, though. So R of minus tau is equal to R of tau. And if it's a complex signal, there's a conjugate thrown in there, but still, it's, for our cases, it's symmetrical, even symmetry. If the signal is not periodic, which we don't really have any signals like that. As the lag goes to infinity, what we get for the autocorrelation function is the DC power, because that's the average value of the waveform squared, which would be the DC power. Random signals would have that property. If it's periodic, though, then you get the autocorrelation function being periodic. So it just repeats itself over and over again with the same period as the periodic underlying signal itself. And the last property is one I talked about last week sometime about signals in general, namely that when you have a spectral density like we do here, you have to have it be non-negative. It cannot be ever negative, because then you could integrate a section of the power spectral density and get negative power, which would be like you'd have a signal generator that can produce power, you'd have a source of power because it's feeding it back out. I just have a mental view of it. If you could have negative spectral density, you would have like a source of energy that would solve our world energy problem. I don't know if you guys smile about it, but politicians love to talk about it a lot, and it's just not an easy problem, I don't think. Where do we get energy from? We have it stored on our planet, but might we say the sun was responsible for generating all the fuels because of the plants that grew? And do you ever talk about that in a physics class? A little bit?
The issue is that we're a far enough distance from the sun to where the density of sunlight isn't very high, which is why we're still alive.
Yeah, so that's like a...
So you can't harvest very much.
Yeah, but in terms of what is stored here, though, right now is still usable, but we can't... You're saying we can't create very much.
No.
Yeah.
That's why we're...
It's kind of a paradox, though, right? That's the paradox part. If we were closer, we wouldn't be alive. So it's just, I don't know. I have problems with politicians saying we're going to have renewables, but I don't know.
If we could find the lossless medium for energy transfer, we could toss a massive solar panel out into space and send it back.
Yeah, and that's, believe it or not, that's been talked about quite a few years ago. We're going to have collectors out there, and we're going to beam it down to the Earth with microwaves.
It's got to be very careful when you just stick it.
Exactly. So it's like being in the path inside a microwave oven and getting fried with that energy.
Like a 1 megawatt microwave.
Yeah. But see, if we burned up all that energy on the Earth, we'd probably have a bigger greenhouse problem. I don't study that for my occupation, but it's just not, maybe I sound like I'm negative, but I just say it's not an easy problem. It's not easy at all. Go backpacking, live as a minimalist, and you still end up using energy. You have to take some supplies along with you, but that's getting down there where I think we could sustain better if we all lived very simple lives.
But I like video games.
What's that?
But I like video games.
Oh, so you'd have a solar panel to charge your game player up, right?
Yeah, it'd be a pretty big solar panel.
I'm not here to answer to solve that problem now. I just find it amusing that some people think it's really easy. I guess if you believe what somebody's telling you and don't try to analyze it, maybe you're happy. Okay. So let's look at some examples. And this is the key to working at least 3 of the homework problems, if not more. So consider a sinusoid signal. A cosine 2 pi f naught t plus theta. It's periodic, so we can use this definition to get autocorrelation, the one that I have red outlined there. So we go in and multiply x of t times x of t plus tau, and then use the trig expansion of that. We have cosine times cosine, so we have cosine of sum plus cosine of difference with the 1/2 factor. And we're integrating over one period. So we know that when we integrate a cosine, over integer periods, what do we get? You get 0, right? Because it's half positive and half negative, so you get 0. So that would be this term right here. This has got the 2f naught in it, so that term's going to integrate to 0. The one that's just a function of tau is the only one that survives because that's a constant. So we get out a squared over 2 cosine 2 pi f naught tau. That's the autocorrelation function. So pretty cool the way this is going to work out. You can see it right here.
Don't even do an integral.
You actually don't do an integral. You have to multiply by the length. But then you Fourier transform that. That was the other step over here, right? You get the autocorrelation function, then move on to the power spectrum by Fourier transforming. And then we use our delta functions in the frequency domain. And we get the 1/2 factor. Again, when we Fourier transform a cosine, remember, cosine has the extra 1/2 from the positive and negative exponentials. And there we have what we were kind of hoping we could get, that we would have the power symmetrical at the positive and negative frequencies. When integrated, it will get back to a squared over 2. I mean, we can do this and say tau equals 0. We get a squared over 2. That was one of the properties. Integrate this. Evaluate the delta functions where they turn on. We just get a squared over 4 plus a squared over 4, so you get back a squared over 2.
The delta is just 1, right?
Right, its area is 1.
So it just goes away.
It goes away. And you have 2 of them now, so you get back.
Oh, you get 2, right.
Yeah.
Okay.
This is a little added theorem that I wrote in the notes that I'm not sure is in the book, but it's kind of helpful, especially in the lab. It can be helpful, I think. It just tells you that you add a constant to a signal and the autocorrelation function comes flying back out of x, but you get a constant term, so you get a DC component added. So you get a squared, and then if the signal has a DC value, that gets thrown on top of it. That's just pretty straightforward analysis. One that's probably even more interesting to look at, and that is that if you time delay a signal, the autocorrelation function doesn't even know. It can't tell. It's blind to time delay. It's still the autocorrelation function that you started with, which makes sense. It's like if my 2 hands were here sliding back and forth, and then I walk the whole thing down here, it's still got the same relationship to the lag. That's the only thing that matters. It doesn't matter where it sits on the axes. Sound good? In statistical signal processing, that has some bad things in multipath, but it's just the nature of what's called a second-order statistic, which is what an autocorrelation function is. Those of you in Province Stats now, you'll eventually be finding averages of one random variable times another, and that's called a second-order statistic. And this is like that calculation because it involves x times x. Okay, extending the one sinusoid to 2 sinusoids, as long as the 2 frequencies are not equal to each other, and if they are, you have to use the phasor addition formula again, right? But if they're not equal, you just would expand this thing out, and you get 4 terms that you would expand out then. Notice I'm taking, this is the composite signal, so this is y, and then this would be y of t plus tau. So when you blow that out, so to speak, that's my way of looking at it, the math blows up. That's why I use the term blowing it out. You're making it bigger because you're getting all those cross products in there. So you have 4 terms, but thinking back to what the time average is, the terms that involve the dissimilar waveforms, like this one and this one, those are at different frequencies. So if those sinusoids are ticking along at different frequencies, and I think of the time average is going from minus to plus infinity, I'm not going to be getting any frequency component at DC when I multiply x1 times x2 because their frequencies are not equal. So those averages will always average out to 0. Does that make sense? There was another proof of this in the Jupyter Notebook for just in the time domain alone, but those time averages are 0. So you get this nice little property that says that the autocorrelation of the sum of sinusoids is the sum of the autocorrelations as long as the frequencies are not equal. And that holds for any number of sinusoids, actually. Then you go into PN sequences, and this is kind of a special case that you study in the lab, in particular, pseudorandom noise. And I'm trying something different. I'm not having this problem turned in this time. It's always been kind of a sticking point. I will talk about it in this class, though, and it'll be in the solutions that I'll be putting out late tonight, so you'll have the solution to it already. So those of you in the lab, since you have to do this as part of the lab, you're going to just have to look at the solution and look at the problem, study the problem some more. And because of my cumulative technique now in posting, if you want to get the sum of everything, you will now take the preliminary solutions that I'll post up late tonight after my jazz band gig at Retirement Center, so it'll be late. That'll have everything in it. That'll have the assignment, the hints page, and then it will have the solutions after that, right? That was Colton's request, because he only has one monitor. I can relate to that.
Yeah, my laptop's not happy this semester.
Well, but Windows 10 or Mac, you can have multiple desktops. I just use the buttons and slide my desktops back and forth. Or does that make you dizzy?
That's big. I don't have enough RAM.
What's that?
I don't have enough RAM.
Oh, really? Okay.
I gotta eat that.
Does anybody else use multiple desktops to see screens? I use it all the time, so.
Since my last Ubuntu build.
Well, you can have it on Windows 10 and on Mac. It's just,
Yeah, the Windows tab button, you can do virtual.
you hold two keys down and then you use the arrow keys and you roll back and forth between your different desktops.
That sounds dangerous. It's like my.
That's what I'm doing
it's like
here,
my-
though.
It's like my Chrome tab. You know what I mean? Like,
Yeah.
I got 3.
You're just asking for like offload
no.
the hardware or off your RAM.
I do way too many dumb things to try and juggle like that.
So a pseudorandom noise generator is an example of a periodic sequence as well, and it's a logic circuit thing. It looks like this using D flip-flops. It's a pseudo noise is what PN stands for, and the typical PN generator, pseudo noise generator, is what's called an M sequence, which M stands for maximal length, and the maximal length has to do with how the taps are taken on the generator. Here, the taps are taken from the last 2 stages, but it varies. I'll just jump down here. It varies from generator to generator. I've got it written up in Python. I have the M sequence, and here's the code of how the taps are obtained. And I think I might have, I guess I don't have the table in here. I think the table is in the lab. But there's the taps. Tap settings. These are the taps here. Then the code just does the rest of it, and I just have certain generators. You can type PN code or M sequence into Google and you'll get some Wikipedia page or something that talks about these generators. Why am I so enthralled by them? It's because in digital comm you need a source of synthetic data bits, so they're used as a pseudorandom pattern in digital comm testing. They're used in frame syncing. They're used in GPS, uses pseudorandom sequences. Each GPS satellite is assigned a different pseudorandom spreading code. 3rd generation cellular used it in CDMA. So the M sequence or the PN generators are quite popular. So the reason why I emphasize this so much in the class, though, is that once you have one period, you should be able to Fourier transform that one period using the theorem we were talking about earlier. But as the M sequence gets longer and longer, like up to 1023 bits long, so it's a 10-stage generator. Are you going to want to Fourier transform this long sequence of 1s and 0 bit patterns? It sounds very painful. Yes, we could do it numerically in Python, and I've got that in the Jupyter notebook already, but it turns out, and this is just taking it on faith, but it can be proven mathematically, that the autocorrelation function for this generator looks like this. So once we have that, getting the power spectrum is just Fourier transforming it. So that's the character of the M sequence. M is the number of registers. It's the number of, it's the period of the code. So M is, write it down here, M is equal to 2 to the n minus 1. So n is the number of shift registers that you have. And then the period is going to be the clock rate, or the clock period times m, so that makes it 1 period. And how do you Fourier transform this? Well, you'll see in the solution, what I have recommended in the hints page already is that you just slice this out of here, and then you've got a triangle. You can do it a number of ways, but the way I think is the best is to say you have a triangle like this that tops out at a squared plus a squared over m, because that's the full height of the triangle. And then you have a second component, which is a DC component that just drops it down. So you have to sum two Fourier transforms together to get the answer. But the level shifting part, that is just going to add in a DC component. So that just modifies the DC spectral line in the Fourier transform, because it's just taking the waveform and taking it on a different pedestal, taking it off its pedestal.
Is there anything else you wanted to try to go over for the homework specifically before class gets out?
Yeah, I'm looking at my clock and I'm saying, yeah, it's running down. I was going to go into the notebook, but I'm not sure that I have to. I've got this in here. I guess it makes me type the password again. So this is right off the website. I'm using my pen. Is this pen working out okay? I mean, it's a new thing for me. I'm kind of getting into it. I'm now liking it because I don't have to type things out. I can just start writing, but I have to try to be neater. But it's really cool because I can, if I find a mistake, I can erase it and just write it again, and I don't have to do anything. I can.
We are judging your penmanship. Just
Yeah. You're a drafting kind of person. You have nice penmanship because you've been doing it how many years?
I'm not telling you that.
Okay, that's a trade secret.
No.
Yeah.
I've
You've been practicing
yeah,
now.
about 15 years.
Okay.
Experience.
At any rate, so problem one is just this theorem that we've already done, and I did talk about that. Are there questions on this one? This is one you have to turn in. You just apply that theorem, and then you can use the line spectra plotting function, which is in. It's over here in down in here. Let's see. I've got two PN sequence examples in here, but here's where I do it down here. This is a numerical one, I think, but the way I'm suggesting that you do it is you just get Fourier transform one period, and then you can get the Fourier coefficients that way, and that's kind of what I allude to up in here, and I do a better job of alluding to that down in here. Or I give an example of a pulse train. This is not power spectral density and autocorrelation. This is just simply saying, okay, there is the Fourier coefficients for that pulse train, and I can just slap them right into the line spectra function. And if the pulse train is not sitting on 0, which is the case of the PN code, it's still the same Fourier transform. There it's the autocorrelation, here it's just the signal, but it's still the same Fourier transform theorem that we're talking about for periodic signals. So if this thing is dropped down on a pedestal, that lowered down, it's now going to have a different DC value. So what I say you can do is after you fill the array up here with all of the coefficients from the unshifted vertically waveform, you can just go in here and load in a different value at xn of 0. Does that make sense? And that's just going to change the spectral line at 0. So then when you draw the picture, it looks like that. And that was one of the key differences in the last week's homework. If you look at my solutions there, you'll see that when you had those two pulse trains, they had identical amplitude spectra, but their DC components were different because their average values were different. So one had something different sticking out at 0. 2 is also being turned in. Here you're just going to be using this statement for power spectrum from autocorrelation. 3, you're also turning in. This is just using theorems and transform pairs. I didn't really have much of a hint for it because it's just, the only thing that's special about this one is you're going from frequency to time, but it is a pure Fourier transform problem. It's just frequency back to time. So you just read the table backwards, right? And use the theorems backwards. So there's not really a whole lot to say there. What else, since I'm out of time? Any other questions?
I'll email you tonight.
Okay. You know, like I said, I'll be playing starting at 6:30 and then a rehearsal after that.
I'll be working on this till 1 or 2 in the morning, so.
Okay, that'll exceed my time limit, I think.
Yeah.
So the quiz, I'll have to write what I'm thinking about for the quiz, but do you have any suggestions? It won't be the last problem, which is linear systems, because we haven't started that review yet, but I'm thinking right now that the quiz can repeat at least half of what you just did on this quiz. Wouldn't you say that would be reasonable? Take another run at that?
I'd like to take another shot at it, that's for sure.
Yeah, I won't tell you whether it's the upper half or the lower half, but then it might be sinusoid and autocorrelation function to get the spectrum that you're working on in the homework right now, like the examples I just did in class. And that can be forwards or backwards. I can give you the spectrum, go back to get autocorrelation, go back to the time domain. I mean, there's like different steps in there that you can take a look at. Okay, have a good afternoon. I wish it was warmer out. I'm sad that I can't ride my bike because it's just too cold out and I don't want to crash on the snow.